I'm Henry Wu from the Call Switch group at Pete and Robin. So today I'm going to talk about Jericho4 for the scale across data center. So there are multiple ways we discussed to scale and build a large AI cluster. So scale up is going to connect XPU within a rack or among adjacent racks. And scale out is going to connect the rack's port cluster within a data center building. And scale across is to connect buildings, campus, or even regions together. And all of them is essential for the AI scaling. So now let's take a look at what the scale across looks like in the practice. So this is a data center map in the United States. And actually, we filtered with the power capacity 10 megawatts or above. Every circle represents a data center. The bigger the circle, the higher the power capacity. So instead of having a lot of big circles, as you can see here, in reality, there's a lot of smaller circles and clustered together. The reason is because the power and space capacity limitations for a given facility. So the leading Gen AI company has been grabbing the computation capacity wherever they can find and interconnect them through a high-speed network. There must be a strong infrastructure to enable the distributed training. So what's the answer? The answer is Jericho4, which can enable the XPU to an unmatched level. So the latest AI model can easily have billions, even trillions of parameters and demand enormous amount of data for the pre-training. So with a large AI cluster, you can apply all kinds of parallel mechanism to greatly reduce the training time. And with the rising of the reinforcement learning, so basically the different data center buildings, they can contribute and improve the model intelligence asynchronously during the post-training. But with such kind of scale, for example, 1 million XPU in one cluster, with such kind of scale, the challenge grows significantly: load balancing, congestion control, traffic management, and security. All is becoming essential and critical. So now let's take a look at how Jericho4 is going to address them. So basically, there are 4 pillars in the Jericho4 answer. Number 1 is the scale. So basically, with Jericho4, you can build up a single system with 36K number of ports. So the single system means it's a non-blocking and single routing domain within just to behave as a single gigantic silicon. So all the complexity, such as load balancing and congestion control, is going to be handled natively by hardware. And the second is really about the single fastest port bandwidth. We call it HyperPort. So this is 3.2T fat pipe. We call it fat pipe. This is 2x what's its latest Ethernet port, 1.6T. So basically, inside a HyperPort, there's no hashing, there's no collision. So it is a native answer to the elephant flow from the AI workload. And the third one is really about the distance. With the embedded deep buffer from Jericho family, so we can easily address more than 100 kilometer lossless RDMA interconnection.
I'm sorry, can you say that one more time? You said 100 kilometers?
Yeah, more than 100 kilometer.
Okay.
Yes, with the deep buffer. So we are going to address that later.
Thank you.
Yeah. And the last one is about the security. We have the embedded security engine. So therefore, you can turn on security for all the front panel ports without any performance impact. So we have multiple derivatives in this Jericho4 family. So we have Jericho4 itself, which is aiming for the modular system. So you have half of the bandwidth for the front panel port and the other half to the fabric interconnection. And we also have the Qumran 40 device aiming for the centralized system. So this is a 51T centralized router. We have a 100 gig SerDes version and also 200 gig SerDes version. So the device has been sampled to customers starting from the beginning of last month.
So a quick question, when you say 64 or 36K ports in a system, do you mean in the complete network?
No, it's just a single system, single domain. So you can, logically, this is just a gigantic silicon. I'm going to cover that in the following page.
But,
yeah.
Okay.
I know it's hard to imagine.
Yeah.
Question on the You mentioned within the past month. Does that match up with any change in the object market that's happened? Like the reason that we can now do it between data centers matches with?
Yeah, actually, the SerDes we used in this Jericho4 family actually is reused, shared with the Tomahawk family. So it's the same SerDes core with such as Tomahawk 6, as Pete showed here. So basically, we see the demand from customer. They want to have 100 gig version in case some NIC endpoint they only have support 100 gig, and some demands with a 200 gig to matching with the latest NIC capability. And also with the 200 gig version, we support the 1.6T Ethernet port. Now let's zoom into those 4 pillars one by one. First of all, it's about how to scale as a single system. So basically, we have multiple form factor. So you can start to build in Jericho4 with a very compact piece of box. It's a 2RU piece of box, 51T, and it can be either 64, 800 gig or 32, 1.6T. And for the middle side, on the right-hand side, basically customer can build up a modular chassis. Therefore, the radix will be much bigger. For example, with a modular chassis 16 slots, you can have more than 500 1.6T or 1,800 gig E from a single modular chassis. And basically, if you want to have an even bigger scaling, you can physically disaggregate the modular chassis, the line card and fabric card into multiple pieces of box, as shown in this middle picture. So basically, we have the line card device, we call it Jericho4, and we have the Ramon device for the fabric piece of box. And you can interconnect them through the standard Ethernet optics. So basically, it gets rid of the physical dimension of the modular chassis to enable up to 36K number of ports. And each port is 3.2 terabit. So why we call it a single system? The reason is because no matter it's the modular chassis or we call it the DSF in the middle, and also the piece of box, no matter which form factor, they basically work together as a single gigantic silicon. See, this is a non-blocking domain and single routing domain. So, for example, in between the Jericho4 and the Ramon, it has the native packet spray. It has native spray and also the end-to-end scheduling. So all those challenges we discussed, for example, the congestion control, load balancing is going to be handled natively by hardware. And therefore, the direct benefits is that it hides all the complexity by the hardware, and you can attach all sorts of endpoints. It can be a very high performance AI NIC. It can be a very simplified, low cost NIC.
And just to clarify, when you say a system, you mean a global system?
I mean a single device. A single device.
It acts as a single device.
Yeah.
You're looking at a bunch of boxes
I
with
understand
cables.
it acts as a single device, but are you talking?
Physically, it's a system. Physically, but
Okay.
logically, it's a single device.
Okay, it's a global system, potentially.
Yeah,
Rack to rack,
Yeah.
between data centers
Okay.
and so forth. No?
actually, you can use, for example, in the middle, the DSF, we call it a distributed scheduled fabric. So it can be a single system to connect up to 36K endpoints in the AI cluster. It can be within a building or across a different building.
Okay, a system is a very nebulous term, so I was just trying to figure out the scale of what you're talking about.
Yeah, the scale, for example, for the regular Ether, for example, for Pete talked about Tomahawk 6, a single device is 100T, right? 100T. You can have 128, 800 gig E. But for this single system, it has 36K number of ports.
It's like as if you had some monster node with
Yes.
with
Yes.
36,000 ports in it. The physical architecture of this, is there any? How involved is that? Is that is there a fair amount of work that needs to go into a physical architecture to enable the single system, building to building, rack to rack, whatever it is?
Yeah, actually, no matter which form factor has been field proven. For example, the DSF, we call the distributed scheduled fabric, has been deployed by Meta, and they publicly announced their deployment since last October OCP. And in the recent public talk, they shared more information regarding their deployment scale and also the performance. For example, Meta mentioned that they built up the multiple AI zone with DSF. Each AI zone has 18K 800 gig E, and they interconnect multiple such kind of AI zone into an even bigger cluster. So basically, the pizza box is very mature. The modular chassis, all of them has been more than a decade. And DSF actually is started from probably around 5 years ago, and has been field proven by the service provider and also the AI space. Basically, the scaling doesn't stop as a single system. We want to, in a lot of cases, we want to scale across as a fabric. So basically, no matter the form factor we talked, it's either a pizza box, modular chassis, or the DSF. They can be a basic building block, and you can combine them flexibly to build up an even bigger fabric. So in this example, we have 2 tiers of the chassis to build up a 2-claw fabric architecture, as each chassis supports either 500, 1.6T, 1K 800 gig, or 2K 400 gig. We can easily address 2 million 400 gig endpoints or 500,000 800 gig endpoints. So this is basically simplify the network in a great way. So instead of having multi-rail, multi-plan, you can have a single rail, single plan for most of the AI scale requirement.
And that's a non-blocking fat tree flow network there?
Actually, inside each modular chassis, it is non-blocking. But in between, where you need to run the regular ECN, DFC, congestion control mechanism. Because in between of them, this is just a standard Ethernet.
Right.
Yeah.
Yep. I guess what I meant to ask maybe was full bisectional bandwidth through that. Okay.
Yeah, yeah.
It's great.
So we continue. Now let's take a look at how the HyperPort works. So in a traditional way, so we aggregate multiple link members through ECMP or lag. And those flow is going to be hashed and pinged through one of the members. The drawback is very clear. You have flow collision and also the hashing polarization. So for example, in this case, if we have 5 flow, each is 500 gig. So the 5th flow is going to overflow, and you are going to have 200 gig packet drop. And another example is 1.6T elephant flow. That will be is going to be pinged through one of the member, and only half of the capacity going to pass through. The other half is going to be dropped. But with HyperPort, we build up the HyperPort based on the standard Ethernet technology. So we reuse the standard Ethernet SerDes, the PCS, and MAC. And on top of that, we just put a glue layer to aggregate 4 of the 800 gig into a bigger 3.2T pipe. Inside the HyperPort, there's no hashing, there's no collision. So every flow is going to take advantage of every member. So because of that, so on the transmission side, we do the packet spray. On the receiving side, we do the reordering. So basically, we can make sure to deliver in order for every flow for the downstream devices. So we observed more than 70% link utilization improvement compared with the traditional way, either ECMP or lag. So which results with a much less training time. Now let's take a look at what is the distance implication. So basically, for the XPU in the scale out or scale across network, they address and access the remote memory through the RDMA protocol. But the fundamental assumption for that is the network has to be lossless. Basically, but the distance actually has a lot of implication over the lossless. For example, the light speed in fiber, the propagation delay is 5 microseconds per kilometer. And 100 kilometer, the propagation one-way delay is half a millisecond. So the round trip will be 1 millisecond. with 800 gig traffic endpoint. So basically, the round trip buffer demand will be 100 megabytes. And we assuming a 51T device on both ends. So even just the on-flight traffic will be 3.2 gigabytes. So this amount of number actually is not possible for the on-chip buffer. It must be addressed by the deep buffer. So the Jericho family actually has the deep buffer support decade ago. So we started from the DDR-based technology and evolved to the HBM-based technology, starting from Jericho4. So this has been field proven in the server spreader and the DC backbone, and it is the same technology, and we just reapply and use it for the AI scale across. So basically, one of our customers is building the world's largest RDMA deployment over 100 kilometers. Now let's take a look at how the buffer actually works. So basically, the nature of the AI workload is very bursty. There are many different reasons to create a burstiness. For example, for a single model, for basically you have multiple different dimensions, and those dimensions is going to compete for the network. Right. And in case you have a large cluster, you may run different tenants or different tasks. So those tasks or tenants, they are going to collide and create a congestion. So the buffer in the network switch must be designed to embrace and handle such kind of burstiness. So inside Jericho4, we have two different types of buffer. We have the on-chip buffer, OCB, and also the HBM deep buffer. So the on-chip buffer is going to handle most of the case to guarantee the low transient latency. But in case there's a congestion, the deep buffer kick in to absorb those burstiness to make sure are lossless. And on the right hand, we take a look at the logical view on the buffer. So for example, when the congestion started, we want to kick in the ECN as soon as possible. Therefore, we can use ECN to slow down the transmission. But the moment you start ECN to the moment it takes effect on the sender, it takes at least one round trip time. So the round trip time is dependent on the capacity and also the distance. It scales linearly with the distance. The longer the distance, the bigger the buffer you need to host.
So if I can ask, do you have, based on your experience in AI, do you have a guidance with, based on the distance and buffer size and everything else, what is a guideline for maximum distance between clusters or data centers?
Yeah, actually, it depends on the user requirement. But from our buffer perspective, we can support even more than 100 kilometers, no problem.
Right.
Yeah. So basically, we can support a few hundred kilometers very easily because we have very deep buffer in the Jericho4.
Henry, we're over time, so I need you to wrap up as soon as you can.
Sure. And just to finish this page, so basically and when the congestion persists, eventually we need to have the PFC turn on and to make sure the lossless. So the moment the PFC is turned on to the moment it takes effect, the buffer has to absorb all the on-flight traffic. This is also scalable with the distance. So the longer distance, the higher the on-flight traffic you need to absorb. In the previous example, we show 3.2 gigabytes. So no matter what, so you see the matrix, you see the mass. We need to make sure the buffer is deep enough to accommodate for a longer distance. Okay, so when the fiber goes beyond the building, so user will have much less control. So it is critical to protect the valuable AI training data. So the Jericho4 has an embedded security engine. It can enable point-to-point MACsec and end-to-end IPsec. So there's no impact on the performance or the training. So to summarize, basically, I think we have seen this page in probably piece slides. Ultra for the HPC and the scale up, and Tomahawk 6 for the up and scale out, and the Jericho4 for the scale out and scale across. So the deployment can be very flexible. So user will be able to use Tomahawk 6 for the scale out inside the building and scale across with Jericho4, or you can use Jericho4 all the way from scale out to scale across. Both of them has a lot of customer deployment. So in summary, so the distance actually you must be addressed with multiple aspects. So number one is the scale. So we have 36K as a single system. Number two is you need to have an answer for the elephant flow from the AI workload, which is addressed by the HyperPort. Then we have the deep buffer to address the longer distance and the MACsec IPsec engine for the security concern.